Good evening, sir. We are Group A from S1G2. Would like to present our assignment about the potential lung cancer predictor. So I would like to introduce our overall of about overall of our assignment first. The lung cancer is the leading cause of cancer death, with over 2.2 million new cases in 2023. And this project will be develop an AI model for earlier and accurate lung cancer prediction using a comprehensive dataset from Kaggle, which will be including the attributes like age, smoking habit, and clinical symptoms. Then the MATLAB MPR tools will be used for model training and validation. To evaluate the effectiveness, we will be using the confusion metric, RC curve, and perform plot. And this will be highlight the potential of machine learning for non-invasive, cost-effective lung cancer diagnostic. So now I would like to explain about the flowchart of our assignment. At the beginning, we need to load the lung cancer dataset from our local device and then convert the potential attribute from the character to the numeric. And then identify the numeric column and select only numeric column and exclude the last column if it is a potential. Then we need to open MPR tool in MATLAB. Then select import data and set the amount of the data for training, validation, and testing. And we can load the dataset we has read into the predictor and response. Then we can start the data training. And then we need to check the result of the training. And if the result of the training is good, then we can terminate the data training. If the result is no good, we need to keep reset and retrain the data and the model until we get the good result of the training.
Here I want to present about the learning process. We see first about the data description, the feature we use in our model. First we have the gender. The gender we use the representation by binary, which one for male and two for female. Versus the second one is age, which we use numerical, which number. Third is we use is smoking, which represented using the binary, but one is for yes and two is for no. Four is the finger, also using binary, same like smoking. Five, anxiety, also using binary. Next is peer pressure using binary. Seven is chronic disease, also using binary. And eight using fatigue is using binary. Nine also using binary, allergy. 10 wheezing using binary. For the 11 is alcohol consuming, also using binary. 12 coughing, also using binary. 13 shortness of breath is also binary. 14 swallowing difficulty, also using binary. And 15 chest pain, also using binary. For the dataset ratio, we set it to 70% for the training data, 15% for validation data, 15% for the testing data. The model we use is using the two-layer feed-forward. We use all the 15 feature from before to our model. The hidden layer have a 10 neuron hidden. The output layer will be the potential which indicate that whether the patient have lung cancer or not. So it will be yes or no.
Okay, moving to step-by-step learning and analysis using neural network pattern recognition tool. Okay, I will explain the code part first. Okay, first, of course, we have to load our preprocessed Excel data using readable. Then we convert the final column, which is the potential column, to numerical using grp2 IDX. We convert yes into 1 and no into 0. Then we assign all the data under the features or the symptom into input, and all the data under potential column as our target. This will is our next step, which is to set the predictor and response. Then finally, we'll use NPR tool to visualize and train our neural network. After click run to our code lines, now the neural network pattern recognition section will appear. Now we simply have to import, then click import data. Then we can import data from our workspace. The input and target that we already set in the code section. We just click row for observation, which set the double array of how much our data with how much our pictures and the classes for the target. Then just click OK and proceed. Now we can do our data ratio adjustment. We can set how much for our training data, validation data, testing data. We simply set our validation data 15 and test data 15. And also we can set our layer size, which is our hidden layer. We set it 10. Then after we done do the adjustment, we can just simply click the train button and the result as shown in our slide will be appear. It will show our model summary, all the data, the predictor, the response, the data division, the training algorithm performance, and under there we will see the error for each data, the training data, validation data, and testing data.
We see the result for the training state. For the first graph, we see that it is a gradient versus epoch graph. The gradient means that magnitude of loss function as the model length. Epoch is a complete pass through the entire training dataset. At the beginning of the training, which means at the epoch 0, the gradient starts at relatively high value. As the training progresses, the gradient magnitude decreases. This indicates that the network parameters are converging to a set of values that minimize the loss function. At epoch 19, the gradient is 0.016668, suggesting that the training process is stabilizing. The decreasing gradient also indicates that the training process is working as expected and the model is learning. If the gradient remain high, it might indicate that the model architecture have an issue. For the second graph, is validation fail versus epoch. Validation fail means that number of instances where the model does not improve over certain of epoch. Initially, the validation checks are low, indicate that the validation loss is not increasing frequently. As the training proceeds, the number of validation checks increase, reaching 6 at epoch 19. The increasing in validation fail indicate that the model performance on the validation set is no longer improving, and this also might indicate that the uh, the model is having a sign of overfitting. Overfitting is when the model is performing well on training data but poorly on validation data.
So now I would like to explain one of the results from our model, which is the performance. And based on this diagram, we can observe that the best validation performance is 0.0x6605 at the epoch 13. And then we can observe that the blue line is used to explain about the cross-entropy error on the training set across the epoch and show model fit to the training data. And then the green line is the used to describe the validation set is used to show the cross-entropy error on validation set across the epoch. And it would be monitors models generalization to unseen data. And then this red line is used to describe the test set, and you used to cross entropy error on test set across the epoch and evaluate the performance on a separate data subset. So based on this overall diagram, we can make some simple conclusion like this model is overfitting indication because the validation error increased while the training error decreased. So this is overfitting.
Okay. Now I will present performance evaluation of our model. We will go through various metrics such as sensitivity, accuracy, and specificity to understand how well our model is performing. Let's start with the training set performance. Our model achieved a sensitivity of 98.9%, indicating it correctly identified 98.9% of the positive cases. The accuracy was 95.9% with 187 true positive with 2 false positive. Moving on to validation set, the sensitivity slightly dropped to 97.6%, but the accuracy remained high at 95.9%. Here we had 40 true positive and just one false positive. For the test set, the sensitivity was 92.5% and we achieved perfect specificity at 100%, meaning there was no false negative. We had 37 true positives and 3 false positives. Looking at overall performance across all set, our data model maintained a high sensitivity of 97.8% and accuracy of 95.5%. In total, we had 264 true positives and 6 false positives. In conclusion, our model has demonstrated strong performance with high sensitivity and accuracy across training, validation, and test set. While the sensitivity on the test was slightly lower, the perfect specificity indicates robust performance. Moving forward, we will be focused on improving the sensitivity further and to reduce false positive.
For our next result, which is the ROC curve, there's four of them: the training ROC, validation ROC, test ROC, and all ROC. For the training ROC, we have the high performance, which have high TRP and low FPR. For this ROC, the curve close to the top left corner and indicate the excellent performance. So it's a great performance. Then for the validation ROC, we have the high TPR and low FPR2, which have a good balance between the sensitivity and specificity. This indicate they change the threshold for specificity. The curve close to the top left, the same as the previous one, is showing a good generative for validation set. For the test ROC, have a similar to validation ROC, which is the high TPR and a low FPR. It have a strong performance consistent with the validation performance. Okay, finally, to conclude all of these ROC, we have the overall ROC. The combination data have the high TPR according the range of FPR. So the consistent performance, model perform well across all the data set.
So now I would like to make a conclusion for our assignment. In conclusion, the model demonstrates good performance with low cross-entropy errors on training, validation, and test set. A neural network model has been successfully trained and validated, as well as achieving good performance metrics, and is ready for deployment or further analysis. And the best validation performance was achieved at epoch 13, indicating the model is well trained. And the scale conjugate gradient algorithm effectively optimized the model, resulting in consistent and reliable classification performance. So that's all from our group. Thank you.